Hi everyone. So in this video, we're going to be returning to a concept that we talked about earlier. So if you remember, in the context of quadratic functions, we learned about these types of numbers called complex numbers. And so we'll be returning to that idea in this video and seeing how complex numbers show up in the context of polynomials. So one thing I just want to quickly mention that you might have noticed, if you're following along in the book, you might notice that we're jumping straight from 3.2 to 3.5. I just want to reassure you that you are watching the correct video. I am intentionally making that jump. What we're going to do is in the next video, we'll go back to section 3.3. I just personally kind of prefer to order things this way. So we're jumping straight from 3.2 to 3.5, but then we'll go back to section 3.3. Okay, so I want to start by reminding you what is a complex number. So we talked about how a complex number is a number of the form a plus bi. And what's going on with these, this a and this b and this I? Well, a and b, those both represent real numbers. And then what is I? Well, I is a special symbol that just is kind of a shortcut for writing down the square root of -1. So just to give a quick example of a complex number, 3 minus 2i is a complex number. You could also have 1 plus the square root of 3 times I. That's another example of a complex number. You could also have a complex number where there's only the I portion. So you could have something like -5i. And then you could even have a number that's actually just a real number. So we talked about this in the last video. It's not super important, but the analogy I gave was rectangles and squares, right? Rectangles are kind of a bigger category and squares are a special type of rectangle. So similarly, complex numbers are like the bigger category and real numbers are just a specific type of complex number. So I could even put a number on here like 1/2. That is a complex number, or 5 or 2 or any real number you can think of that is considered also a complex number. Another kind of designation that I'll sometimes be using in this video is that, like I said, because real numbers are considered also complex, I'm going to designate that 1/2 is a real number. And then what I would call the rest of these is I would call these non-real numbers. So when I say a complex number, that really can mean any type of number. And so I'll sometimes say real and non-real to kind of differentiate between what we're talking about. Okay, so another thing that we talked about with complex numbers is this idea of a conjugate. So the conjugate of a complex number a plus bi is going to be the number a minus bi. So basically for any complex number, its conjugate is just what you get by flipping that sign between the two kind of parts of the complex number. So an example would be that the conjugate of, what did I say here, 3 minus 4i. What's the conjugate of that? Well, it would be 3 plus 4i. So it goes both ways. You can either start with the minus and go to the plus, or vice versa. They're conjugates of each other. Okay, so I want to give you kind of a warm-up to think about here, and this is something that we'll come back to later in this video. So I want you to think about what happens when you multiply a complex number and its conjugate. So the example that you might want to do is the one that we just wrote up there. So for example, multiply together 3 minus 4i and 3 plus 4i. So pause the video, take a minute to try to multiply those together and see how much you can simplify your answer. So you're going to want to kind of FOIL it out the way you normally would with an expression that looks like this, and then see what you can do to simplify your answer. Okay, so what happens when we multiply these two things together? Let's try it out. So 3 minus 4i times 3 plus 4i. So we want to multiply these together by kind of distributing each portion so that everything gets multiplied with each other. So we do 3 times 3, and we get 9. We do 3 times 4i, and we get 12i. So I mentioned this before, but when you're doing something like this, you can almost treat I as though it's like a variable. It's gonna act the same way that like x would in this scenario, with an exception that we'll see at the end when we go to simplify. Then we multiply here and we get minus 12i. And then we multiply these two things together and we get minus 16i squared. So notice that the two middle terms, those both canceled out. And that shouldn't be too surprising. So why did those middle numbers cancel out? Well, because this is actually a difference of squares, right? This is an expression where you're adding and subtracting. And whenever you have a difference of squares, you're going to end up with a plus and a minus term that add up to 0. Okay, so we're left with 9 minus 16i squared. But we can actually simplify this a little bit more. So let's go back to the definition of I, right? I is supposed to be equal to -1, or the square root of -1. So what does that tell us about I squared? So if I is equal to the square root of -1, then I squared is equal to -1, right? And so when we go down here to simplify, instead of writing I squared, we can replace I squared with -1. So we have 9 minus 16 times -1. I'll make a note of that here too. So I squared is equal to -1. And so then this becomes plus, so we end up with 9 plus 16, and we get 25. So it turns out something like this is going to happen every time you multiply a complex number and its conjugate. You're always going to get a real number. And the reason that happens is basically just the way that the conjugate is kind of set up, right? Because one of them is minus and one of them is plus. As we mentioned, it's a difference of squares. The I parts cancel out. And then you have this I squared, but I squared can be simplified because I squared is just -1. And so at the end of the day, once you multiply them together, you don't have any i's left in it anymore, so it's just a real number. So this might seem kind of random, but we'll come back to this idea later and see how this basically is related to finding the zeros and factoring within a polynomial. Okay, so I want to now go into an example to tie this back to what we were doing in our last video. So what I want to do in this first example is I want to find all zeros of the polynomial f of x is equal to x to the 4th minus 2x cubed plus 5x squared. So things are going to be a little bit different in this example, but let's pretend we didn't know that they're going to be different. Let's kind of just jump right into this the way that we did in the last video. So, and I would encourage you to pause and try, see what happens if you try to approach this like we did in the last video. So what do we generally do when we're finding zeros? Well, we want to take our function and set it equal to 0. Actually, let me write it the other way. X to the 4th minus 2x cubed plus 5x squared is equal to 0. So generally speaking, the first thing we want to try to do is factor. So what can we factor out? We can factor out an x squared. So we're left with x squared minus 2x plus 5. So from here we can say, either x squared is equal to 0 or x squared minus 2x plus 5 is equal to 0. And so how can you solve something that looks like x squared minus 2x plus 5 equals 0? You can use the quadratic formula. So we say x is equal to negative b, so in this case that's -2, plus or minus the square root of b squared, so -2 squared, minus 4 times a, so that's 1 times c, which is 5, all divided by 2a, which in this case is 2 times 1. So this is going to simplify to 2 plus or minus the square root of 4 minus 20 divided by 2. And so 4 minus 20 is going to be the square root of negative 16. Okay, so from here you might notice that something is a little different, right? We're now having the square root of a negative number. And so that tells us, if we think back to quadratic functions, that tells us that there's going to be no x-intercepts coming from this portion. And that's an idea that we'll come back to. But we do know how to continue to solve this, right? Just because there's no real solutions, that doesn't mean that there's no solutions. You know, we can keep going and write down complex solutions. So we learned in the quadratic function section that we can rewrite this, right? Square root of negative 16, we can rewrite this as the square root of 16 times the square root of negative 1, which is equal to 4 times I. And so now we can rewrite our solution as 2 plus or minus 4i divided by 2. And so to simplify this, we can factor out 2 from everything in the numerator. Oops, so it's 1 plus or minus 2i over 2. So now we can cancel out our 2, and we are left with 1 plus or minus 2i. Yeah. Okay, so this gives us 2 additional solutions, right? We want to remember that plus or minus each is its own solution. So we have the solutions x is equal to 1 plus 2i, and then we also have the solution x is equal to 1 minus 2i. So remember that when we get solutions from the quadratic formula, those always have multiplicity. So that's something we talked about in the last couple of videos. The multiplicity is going to be 1. And actually, in this video, we'll finally see why that is a little bit later. So each of these has multiplicity 1. And then going back to our other solution we had here, we had x squared is equal to 0. So that tells us that x is equal to 0. And that solution has multiplicity 2, right? Because we had x squared. Okay, so I'm going to circle these up so that we can kind of compare them. So now, remember in our last couple of videos, when we talked about zeros, we talked about them corresponding to x-intercepts. So we have 3 zeros, right? We got x is equal to 0, x is equal to 1 plus 2i, and x is equal to 1 minus 2i. Which ones of these are actually x-intercepts? Well, it's only going to be the real solutions, right? So this is similar to what we saw with quadratic functions. We saw that real solutions gave us x-intercepts. Complex or non-real solutions, they didn't give us x-intercepts. They're still solutions, but they're not solutions that are going to directly show up in the graph. And so this tells us that we have an x-intercept. Actually, let me write something else down first. So this is a real solution. And so that corresponds to having an x-intercept of, in this case, 0, 0, right? Because the x coordinate is 0. And then these are non-real solutions. And so when you have non-real solutions, actually, let me say it this way, they're non-real zeros. And so when you have non-real zeros, that tells you that they are not going to give you any x-intercepts. So they are zeros, but they're not x-intercepts. Let me say it as a 0 here too, just to be consistent with our language. So basically what we were saying about zeros and x-intercepts being the same thing, well, that's only true when you're dealing with real zeros. As soon as your zeros are not real numbers, they just don't show up as x-intercepts. So what do we expect to see in the graph of this, right? So what do we expect to see? We only are going to have one x-intercept, right? Because we only found one real zero. And that x-intercept has a multiplicity of 2, and so that means that it's going to bounce, right? Even multiplicity means it's going to bounce off. We can also kind of determine the end behavior by looking at the degree and the leading coefficient. And so because it's a positive leading coefficient, even degree, we know it's going to have a shape kind of like a parabola. So let's take a look at the graph. So here is the graph of our function. You might look at it and say, oh, it's just like a normal parabola, but if you look at it carefully, it's not exactly symmetric, right? Like you have a point over here, and then if you go directly across, it's not quite symmetric. So really what's going on is that these complex zeros, or the non-real zeros, they are influencing the shape of the graph. They're just not showing up directly as x-intercepts. So we only have one x-intercept, but the shape of the graph, that is dictated by other things such as the non-real zeros. So I just want to make a quick note of what we just said on this first page, just so that you kind of have it all in one place. So basically what we figured out from that example is that some polynomials have non-real zeros. So have zeros that are not real numbers. However, those non-real zeros do not correspond to x-intercepts. So basically, only real zeros give you x-intercepts. Non-real zeros, they're still worth noting, but they're not going to kind of show up in the graph in the same way. There's one more thing that I want to show you with this example. So remember that we talked about how anytime you have a zero, you have this corresponding factor. So let me kind of write that fact down here. So remember that if a number c is a zero of a polynomial, I'll say f of x, then x minus c is a factor. And so we saw how that was true in our last video. We saw that that's the case even when you're dealing with weird solutions, even when your solutions are not kind of nice, clean, whole numbers. And so it also turns out that this is true even for non-real zeros, which is maybe a little bit surprising. It's definitely not the kind of factoring that you're used to seeing. So I want to show you how that actually works out for this example. So what are our three zeros in this case? So our zeros were 0, and that had multiplicity 2. And then we had here for our two non-real zeros, we had 1 plus 2i. And we had 1 minus 2i. And so what is that going to give us as our corresponding factors? Well, for the first one, we'll have x minus 0, which is just x, right? But then it's multiplicity 2, and maybe let me make a note of that. So this one was multiplicity 2, this was multiplicity 1, and then this was also multiplicity 1. So what are going to be our factors? Well, we're going to have a factor of x squared. We're also going to have a factor of x minus 1 plus 2i. Right? Just the same rule that always works. We just subtract our 0 to get our factor. And then what is going to be this other factor? Well, it'll be 1 or x minus 1. Sorry, let me get my other color. 1 minus 2i. So all I'm doing here is just taking the zeros we found and putting them each, subtracting each of them from x to find the corresponding factor. And so if that's the case, then it should be true that f of x can be written as x squared times, and I'm going to now distribute this negative sign on each of these. So this is going to be x minus 1 minus 2i. And then this one is going to be x minus 1 plus 2i. Okay, so let's verify that that is actually true. So how can we check that that is actually the factorization? Well, we can just go and multiply it all out, right? And actually, let me just move this to the side a little bit. So what is the kind of best way to multiply this all out? Let's start by multiplying together these two. So we're going to have x squared times whatever we get when we multiply those two together. Okay, so we want to multiply these together kind of term by term. So we're going to get x squared. then we're going to get negative x. And I would definitely encourage you to pause the video and try this part yourself because it's kind of cool, and I think you'll appreciate it more if you actually do it yourself. Plus 2i times x. Then we go and we do negative 1 times everything, so that's going to be minus x. And then we get plus 1. And then we get minus 2i. And then we finally multiply this last term with everything. So we do negative 2i times x. And then we do negative 2i times negative 1. So that's going to be plus 2i. And then we do finally negative 2i times 2i. So that's going to be minus 4i squared. Okay, so let's try to clean this all up. So we're going to look for things to cancel out. So we see that here we have a plus 2ix. Here we have a minus 2ix. So those can be canceled out. You might also notice that here we have a plus 2i, and here we have a minus 2i. And so those cancel out. And so let's see what we're left with. So we have x squared minus 2x. And then we have plus 1. And then here we have minus 4i squared. And so remember that I squared is equal to negative 1. So we can rewrite this as 4 times negative 1. And so this is going to now be x squared times x squared minus 2x plus 1 plus 4, right? Because we have negative 4 times negative 1, so this is going to be plus 5. And so if we multiply this back together, we get x to the 4th minus 2x cubed plus 5x squared. So let's go back to our original function and see if that is what it was. So it is, right? X to the 4th minus 2x cubed plus 5x squared. So why did this happen? You know, why did this work out that like, it looks like this is a crazy factorization, right? Like we have all these i's and all this stuff going on, but we saw earlier that when you multiply a number and its conjugate together, the result is a real number. So that's really what happened here. Because the two solutions we got were conjugates, they just interacted in a really nice way where at the end of the day, we still ended up with only real numbers in our polynomial. So, you know, it might seem counterintuitive that you can factor a polynomial and have like these i's in there, these non-real numbers, but just because of the way that the solutions come in conjugate pairs, things work out. All right, so I want to do one more example of just finding all the non-real zeros and the real zeros. So I would definitely encourage you to pause the video on this one and try it yourself now that we've already done one. We're not going to do the factorization for this one because I think, you know, seeing it once is probably enough, but I just want to go through the process of finding the zeros. Okay, so how do we find the zeros? We basically just want to take our function and set it equal to 0. And so in this case, to get rid of that extra negative sign that can kind of make things confusing, we can divide both sides by negative 1. And so we get x cubed plus x squared plus 5x is equal to 0. So now we can factor out an x from everything. And so we're left with x squared plus x plus 5. So from here we have x is equal to 0 is one possibility, and let's just write down right away that's multiplicity 1, right, because it was just x, it wasn't x squared. The other possibility is that x squared plus x plus 5 is equal to 0. And so this one cannot be factored, and so the only way to solve this other equation is by using the quadratic formula. So we get, and actually now we know actually that saying something can't be factored is actually kind of untrue. So maybe let me just quickly mention that. We said earlier that this quadratic function or this quadratic expression could not be factored. It turns out it actually can. It's just that the way it factors is kind of crazy. It's with these non-real numbers. So when I say can't be factored, it can technically be factored. Actually, any quadratic can be factored if you're using complex numbers, but the idea is just that it can't be factored like by hand, right? You're not going to look at that and see what the factorization is. You can always find the zeros and then work backwards to find the factorization, but you're not going to see it directly. Okay, so we have x is equal to negative b, so in this case that's -1 plus or minus the square root of b squared, so 1 squared minus 4 times 1 times 5, all divided by 2 times 1. So we get x is equal to -1 plus or minus the square root of 1 minus 20 divided by 2. And so this simplifies to -1 plus or minus the square root of -19 over 2. And so this one can't be simplified as much as the other one. So the square root of 19, or -19, that can be written as the square root of 19 times the square root of -1. And so that's just going to be square root of 19i. And so this one can't be simplified as much because there's no factor of 2 that we can pull out from the numerator. So what are going to be our two zeros? Well, we get x is equal to -1 plus the square root of 19i over 2. And then we have also x is equal to -1 minus the square root of 19i over 2. And so as we said before, each of these zeros has multiplicity 1. Okay, so I want to just take a quick peek at the graph of this function, but before we do that, let's just quickly think about what we should expect from the graph. So we found 3 zeros. However, 2 of those zeros were not real numbers. So we really only have 1 real zero, and so this is going to give us an x-intercept. So we're going to have an x-intercept at the point 0, 0. We're not going to have any x-intercepts from those other ones. In terms of the end behavior, we see that has a negative leading coefficient and an odd degree, and so it's going to have a shape like the graph of -x cubed. So it's going to be going kind of from the top left to bottom right. So let's take a look at what the graph actually looks like. So this is actually kind of a boring looking graph. It almost looks like it's a line. I promise you it's not really a straight line. If you look really carefully, you can kind of see like a slight bend in it. But this is just what generally happens when you have polynomials that have non-real zeros. Because they have fewer zeros, the graph just doesn't kind of bend around as much, right? It just doesn't have as many opportunities to kind of pass through and go back up and things like that. And so that's why it kind of looks like a straight line. All right, one last thing for this video. And so this is something that is called the fundamental theorem of algebra, which sounds pretty intense, right? I'll let you decide how fundamental it feels to you. But it's a cool fact, and it's a fact that we really can only be aware of now after this video, after learning about complex zeros. So the fundamental theorem of algebra basically says that the degree of a polynomial, any polynomial, this is everything we're writing down is going to be true for all polynomials. So the degree of a polynomial is equal to its total number of zeros. And so in order to make this work, we need to include non-real zeros. And we also have to count including multiplicity. And so I'll show you what I mean by that in a moment. Okay, so let's actually just look at the first example that we did in this video as kind of an example of this. So the first example from this video was the polynomial f of x is equal to x to the fourth minus 2x cubed plus 5x squared. And so we found that the zeros were 0, and that had multiplicity 2. We also found 1 plus 2i, and that had multiplicity 1. And then we also found 1 minus 2i, and that also had multiplicity 1. So what do we get if we add together all of these zeros, counting their multiplicity? Well, we would say 2 for the first one, right? That's multiplicity 2, plus 1, and that is equal to 4. And 4 is the degree. Why did that work? Why is that the case? Well, what happens if we factor this? How can we see that it's always going to be true that the degree is equal to the total number of zeros? Well, if we factor our polynomial, as we know that we always can do, right? Now that we know about complex zeros, we know that actually every polynomial can be factored. And so if you remember how this one factored, it was x minus 1 plus 2i and x minus 1 minus 2i. So notice that for every 0, we have a factor, right? And we could even write it, instead of writing x squared, we could actually write it as x times x. And so because every 0 gives you a factor, well, when you multiply all this together, how many x's are you going to get? Well, you're going to get 1, 2, 3, 4 x's, right? So the highest power is going to be x to the 4th. So because every 0 gives you a factor in the factorization, that's where the highest power comes from. Just to give one more example, so this is one from an earlier video. So in an earlier video, we did an example that was g of x is equal to 2x to the 5th minus 8x to the 4th plus 8x cubed. So this was actually in the video right before this one. We found that the zeros of this polynomial, so this one had all real zeros, we found that had a 0 of 0 with multiplicity 3. We also found that had a 0 of 2 with multiplicity 2. And so if we add these together, we get 3 plus 2 is equal to 5, and that is the same as the degree. And so just to show you also how this one factored, just so you can really see where this is coming from, well, this one, if you go back and look at how it factored as x cubed times x minus 2 times x minus 2. And actually, let me even write that the way I did it above to really emphasize all these x's. So really x cubed is x times x times x, right? And so what's going on here is that when you multiply this out, how many x's do you have? Well, you have 5 of them getting multiplied together. All right, so that is it for this video. In our next video, we're going to learn about something called polynomial long division and see how that allows us to find some more zeros of polynomials, and that will actually be our last video about polynomials. So I will see you all then.